Okay, thank you, Roy, for the very nice introduction. Good evening, everybody. I'm very excited to talk tonight about our latest product. This camera is not an ordinary camera. It's running an algorithm on board to determine its position and orientation in space. And we believe this can be a game changer for the next generation of robots, drones, as well in augmented and virtual reality, or even autonomous driving. In the following, I'm going to talk about the algorithm running on board and the use of this camera to create an autonomous robot. Roy already introduced me. I'd still like to briefly introduce myself. I'm Phillip Schmidt. I'm a software engineer in Intel RealSense and working on the SLAM sensor fusion algorithm, mostly for robotic applications. Before, I used to work at the German Aerospace Agency, also in space robots, and mostly on robotic vision and control, and obtained my master's degree in control engineering. This is the legal disclaimer. You can read it afterwards. Okay, let's talk about the problem statement first. To be able to fulfill any high-level task, for example, cleaning a room, delivering an object from A to B, one of the most basic primitives is to be able to travel from A to B. And to be able to do that, on the one hand, you need information about the environment. On the other hand, you need to determine your own position and orientation. And there are several applications for this. Could be any kinds of robots, for example, in agriculture, consumer personal robots. One big market are vacuum cleaners, also drones, or as mentioned, augmented virtual reality. I would like to start with this demo video. So this is the robot base, the Kabuki. You might know it, for example, from the TurtleBot. And what we did is we mounted two cameras on top in front of the robot. You might have also seen it in the other demo area. These two guys below the tracking module and above T265 and above the depth camera D435. And I want to point out that most of the perception is running on these two cameras. So here the robot goes off, explores the space, can be a living room, home environment. It's building a map using, on the one hand, the depth data, the point cloud transformed into a common reference frame, and accumulates it over time to create this map. You see here, for example, the couch, the two couch chairs, the table, you see the two legs. It's going around the couch. We have a path planner implemented, so you could just click somewhere on your mobile device, for example, phone or tablet, and send the robot.
Is this real time?
This is sped up to 4 times. Another feature I want to point out is the obstacle avoidance of dynamic obstacles. Could be persons, pets, or other vehicles, for example. And as soon as they enter the field of view, they are, on the one hand, mapped, as you see on the left side, and the path planner replans the trajectory. So then in the following, I'm going to talk about how this robot was built and more about the two cameras. I'd like to start off with a general introduction to the SLAM problem, then give a system overview, talk more about some of the components, the tracking camera, T265, our depth cameras. I want to talk about the robot itself and its kinematics. Then for the integration, the calibration between the cameras and the robot is one important aspect. And I'd like to show 2 sample applications. One simple one, only using the tracking camera mounted on the robot and a position controller to make the robot follow a predefined path in free space. And then on top of that, using the depth camera, D435, to as you saw, let it avoid obstacles and create that dense occupancy map. And I'd like to end the talk with a Q&A. Okay, a lot of you might be familiar with the SLAM problem, simultaneous localization and mapping. It's kind of a chicken-egg problem. On the one hand, the robot is trying to gather information about its environment. On the other hand, estimating its own pose with respect to those landmarks. And in the case of VIO, visual inertial odometry, the focus is on the pose or the motion of the robot over time. And there exists a wide range of different approaches, ranging from dense to sparse, depending on the number of features that are used, direct, using the pixel values, to indirect feature descriptors of some of the image regions. Since it's an estimation problem, iterative techniques are used, such as Kalman filter or batch optimization as bundle adjustment over a limited time horizon, a limited window. Also, people use different feature types, different feature descriptors, and implement additional features such as relocalization, meaning the robot detects when it's coming to the same spot or observing the same scene. That information can be used to either optimize the trajectory and map, or also to make use of a map that was obtained in a previous mapping phase. And in this slide, I would like to talk about benchmarking, which is one important aspect due to the variety of different approaches. I'm highlighting here 2 different data sets. There are many more. One of them is UROC for drones, has stereo pair, IMU, and external measurements to obtain ground truth and assess the accuracy of the algorithm. The other one is Kitty, aimed at autonomous driving applications. Was recorded in the downtown of Karlsruhe in Germany, and that one as well has odometry from the car and uses GPS as ground truth. And while in literature, the focus is mostly on the accuracy of the algorithm. One very important aspect in practice is also the computational resources that are used, especially for embedded systems. And some later publication from ICRA 2018 is clearly showing this trade-off between CPU usage and the accuracy as plotted below, of different methods, different systems. And what we are trying to achieve is basically to get into that lower left corner and reduce CPU usage and memory footprint while maintaining the accuracy. For embedded systems, memory is another important aspect. And for the productization of one SLAM approach, there are many different components that have to be taken care of. Here you can see some of them, ranging from the left side, hardware, drivers, to higher level vision processing functions, and back end, for example, to deal with the map optimization and so on. And this is incredibly hard to optimize that for one system to obtain the best performance. And that is what we achieved with the tracking camera T265. Here you can see a system overview. It uses 2 fisheye cameras and an IMU. And what is important to highlight is that the whole algorithm is running on board on the Intel Movidius Myriad 2 vision processing unit. It is very low latency, low power, has a small footprint, and has before mentioned features: inside-out tracking, appearance-based relocalization, and mapping. One feature I want to highlight for robotic applications is that we can make use of the wheel odometry, read encoder values on the host, and send them to the device to make use of them in the sensor fusion. And here you see the sample output. Basically, out of the box, plugging the camera into your computer. It uses the RealSense SDK which is on GitHub, an open source project, works cross-platform. And this is one of the tools, the RealSense Viewer, the same one that is also used for the depth cameras. And what you can see here is, on the one hand, the different sensor streams. You see the left and the right imager. What I point out is the very wide field of view. It's almost 180 degrees. Those are fish eye, and you can see how the lines bend towards the periphery. You see you get IMU information, the accelerometer. Which is measuring gravity in the static case here. And you see the gyro information, which is coming with 200 hertz, and that is the same rate that we are outputting the poses at, which you see here on the right, the output of the algorithm. And you can see this even better in the 3D view. So what you see here is the camera is picked up, moved on an arc, or for example, that could be on a robot or a drone as well, and is coming back to the same spot to assess its accuracy in terms of loop closure. You can get an idea of the scale by the baseline between the two imagers, which is 6 centimeters. So it is traveling a distance of around, let's say, 1 meter and coming back to the same spot very accurately. Also, what you see here is the trajectory in green, which reflects the confidence level. It is at high confidence right now, and the device or the algorithm can also output medium and low confidence. Talking about the algorithm inside, I mentioned it is VIO, following the nomenclature from the second slide. It is a sparse Kalman filtering approach, and I mentioned the poses are output with 200 hertz and very low latency. That makes it usable for applications such as virtual reality, augmented reality, or also for the control of robots with fast dynamics, such as drones. And in our testing, the accuracy, the loop closure error, was always below 1% of the path length. I also want to highlight the appearance-based relocalization feature. That means it solves the kidnapped robot problem. If the camera is occluded, open again, the robot detects that it is in the same space. It can make use of a map for a space that was mapped previously as well. And what you see up here is again the trajectory, and you see some of the landmarks, some of the features we are tracking. It is sparse and can work with only very little features, only little texture. And this is the API. It is part of the RealSense SDK, as I mentioned. These are the functions that apply to the tracking module. So as you see in the second one, this is the pose frame, that is the output of the algorithm, and it is implemented as callback and can be read with the 200 hertz and used for control or other applications. I mentioned this coming together with a confidence level and also higher order estimates, such as the estimated velocity twist, and the estimated acceleration, which can be very useful for the control. We can also access the raw sensor streams as seen in the viewer, the video frame, accelerometer, gyro frame, which come as a callback as well. The next two functions apply mostly to wheeled robots. I will talk a bit more about the calibration that has to be provided between the camera and the robot, and the data can be fed through and sent to the device. The last part is about relocalization, which can be enabled, disabled. Maps can be loaded and saved, and we also get callbacks for each relocalization event. that will notify the user, and the user can decide what to do with the relocalization. And please go to GitHub. You will see all of this there. You can see the API and examples on the usage. And here's a minimal example. You can see it only takes a few lines of code to get pose information from the device. The idea behind this is that a class is implemented that inherits from the manager as well as the device, and implements or listens to those callbacks, such as when a device is attached. Here in this case, it is started in the default configuration. It can be configured depending on which stream should be enabled, if relocalization should be enabled, disabled, and so on. And for each pose frame, here the information is just print to the screen, can be used in the controller, for example, or for higher level fusion or occupancy mapping. Here you can also directly access the estimated velocity and estimated acceleration. And the same holds for the sensor streams. You saw it before, video, accelerometer, gyro callbacks. For a more complete example, again, please go to GitHub. In this libtm util, you will see more of the functionality, such as loading, saving of maps, and usage of the wheel odometry. So the prior slide, this points directly to the RealSense SDK repository, which is called LibRealSense on GitHub. And this one here points specifically to one sample. Most of that functionality regarding the tracking device, at least the low-level API, is integrated in the third party under libtm. Okay, and I would like to talk more about the robot itself. We already talked about the tracking camera, the T265. I'd like to talk about the other components, the Kabuki robot base and the depth camera D435 mounted on top. And we are using an Intel NUC to control the robot. This is a system diagram on how these components are interconnected. All of them are connected via USB. And we receive depth images directly from the depth camera D435. We receive poses, odometry from the tracking camera. And together, those are fused to build the occupancy map, as you saw in the video. This is then used as input for the path planner and ultimately the motion control, which sends velocity commands to the base. I also mentioned the use of the wheel encoder information, which is fed through here and can be used in the fusion. And in the following, I'm going to talk about the different components in more detail. We already covered the T265. This about the depth cameras. We talked about it briefly. These are the two latest products. There's the 415 and the 435. Both of them are stereo systems, active in the sense that they have an IR projector to obtain a good fill rate, and they have RGB on the side. What is the difference between them? The 435 has a wider field of view, and for stereo systems, there's a trade-off between field of view and the accuracy, as can be seen below. So for this project, the 435 was chosen for its wide field of view to be able to detect obstacles when moving around corners, for example. For other projects, you would probably, such as reconstruction or scanning, you would probably prefer the accuracy from the 415. And there's a more detailed comparison under this URL with the table. Some other differences are, for example, the 415 has the rolling shutter, 435 has global shutter, and there's another addition that has an IMU. the 435i. And this is the sample output, again using the same tool from RealSense SDK, the RealSense viewer. What you saw in the first image was, on the one hand, the RGB, on the other hand, the depth map, color-coded from close points in blue to far away points in red. And these two can be fused to obtain this colored point cloud that you see here in 3D. I'd like to talk about the robot itself. It's a differential drive with a caster wheel, and we are assuming point contacts to arrive at these simple relations. What I want to highlight here, on the one hand, are the intrinsic parameters of the odometry calibration, which is the wheel radius, as well as the distance between the two wheels, basically the baseline. And with this relation, one arrives at a unicycle model that can be used for the control. Despite the simple kinematic model, it only has 3 states moving in the plane and 2 inputs, yet it's a nonlinear model and non-holonomic, meaning to steer the robot to a desired target configuration, one basically has to solve the parking problem, or simply speaking, the robot cannot move sidewards. And I will talk a bit more about the control on one of the next slides. The other important aspect for making use of the wheel odometry is the calibration between the camera and the robot, obtaining the relative transformation. We briefly saw another hand-eye calibration before. This is also a classic hand-eye calibration problem in the sense that it can be obtained from relative poses, but what is different here and why common methods cannot be used is that the robot only moves in the plane and only rotates around one axis, which makes some of the degrees of freedom unobservable. So I wanted to highlight this work from ICRA 2012, which proposes a method to solve this problem. And in practice, what can be done is either using the CAD model from the design, or mount the camera in a known configuration, for example, parallel to the ground, and measuring the translation with centimeter accuracy. And this could later on be refined from the pose output. Then I would like to talk about the first application, only using T265 mounted on the robot to follow a predefined path in free space. For that, a simple position controller can be implemented. The only difficulty here is that the original dynamics are nonlinear and non-holonomic. But I want to highlight one approach here that I found appealing, which is applying a coordinate transformation, basically visually moving the point of interest away from the center between the wheels, and by this making its position controllable. Not only it can move forward and backward, but also to the sides, using the rotation of the robot. And by applying this transformation to the output, as well as choosing new inputs, U1 and U2, this robot can be basically controlled as a point mass. And you can see it here in the video that was implemented on the robot. It is the same robot, it only has the T265 mounted in front and moving in the same environment following a predefined path. So in that case, we just programmed it to follow a rectangle of 6 by 4 meters. And you can use the floor, the tiles on the floor, as visual reference. Each of them have half a meter size. And you see how it is following that line, turning after 6 meters, passing behind the table, and then ultimately coming back. In total, it is doing 2 loops and coming back to the same spot. That we can assess the accuracy by the loop closure error. It is coming back to the same spot after traveling a distance of 48 meters, and is coming back to the same spot with below 15 centimeter, which is less than 0.5% of the path length. Then for the next application, in case of an unstructured space that has possibly obstacles or even dynamic obstacles, we added the depth camera D435 on top and to create an occupancy map. And the idea, I mentioned it briefly before, is to transform the point cloud into the common reference frame using T265 poses and accumulating the points over time. And internally, this is a 3D representation. Only in the very end, we slice the 3D map at the height of interest of the robot to obtain this 2D occupancy map. And the different fields here, the meaning is they have a probability between free and occupied, 0 to 100. And this can be in the next step used for the path planning. And I want to show some sample input. That is the data coming from both cameras. We see in bold the world reference frame here, the pose of the tracking module, and the point cloud. And this experiment was actually done to assess the time synchronization between the two and making sure that none of the objects move during or blur during fast motions, especially rotations. So you can clearly see the different objects. You see the wall, the chair, and so on. And this is the data that was used as input for the occupancy mapping. The output is displayed here that was generated from the same motion, same trajectory. And all of this was implemented in ROS. There are ROS wrappers around all our cameras. Plus what we added on top here was our occupancy mapping algorithm that I explained briefly before. And for that, we also created a ROS package. Some of you might recognize Arvis here. And with this, I would like to wrap up. To give a short summary, I demonstrated some of the main components to build an autonomous robot. I want to highlight that most of the perception is running on the RealSense cameras on board. We talked about different SLAM approaches and the importance of efficient SLAM, and that it is hard to productize it. You saw all the different components. And that T265 actually solves this problem and can be used out of the box. It is very lightweight, has a small footprint, and low power consumption. For robotic applications, we can make use of the RealOdometry, which increases the robustness. And in combination, the two cameras can be used for occupancy mapping and obstacle avoidance as well. For more information, please go to our website. Thank you. Okay, and are there any questions?
Hi.
Yes.
Yeah, I'm Aiden. Yeah, thanks for the talk. I have a few questions. First one is that the most of the depth camera you have, the baseline would be between the 50 millimeter to the 60 millimeters. Why not have a larger baseline, like 120 millimeters? And second question is that in a tracking API, that library actually gives us some raw image data. Are those synced with the IMU so that we can run the external state estimation algorithms? And last question is, why not have one camera give you a depth information and also the tracking information? Why not? Why you have two cameras?
Okay. Maybe Roy can answer the first one about wider baselines. I want to answer the third one right now. And part of that is what we already saw, that there is a trade-off between field of view and depth accuracy. So there are competing design requirements for the two solutions. For the tracking camera, we want a very wide field of view to obtain good robustness, while for the depth cameras, maybe we want a slightly smaller field of view or a smaller field of view to obtain better depth accuracy. And maybe Roy can answer the first question about the baselines.
Yeah, so about the baseline, very valid question. We struggled through it ourselves, went through a lot of iterations. Based on feedback from our first generation cameras, we felt most of our current customers are in this range of about 4 meters. So we've chosen this. Now, we are seeing interest in larger baselines, rather longer distances. So we are evaluating to see whether we should do a larger baseline or not. But at this time, these are only two cameras.
And is the test on your?
We're looking at it. We're looking at it.
Okay, and the second question, I'm not sure if I understood correctly. Please correct me if I'm wrong. I think it was between.
Actually, image should be synced with the IMU. What I mean is a hardware triggered to have an exact timestamp. So what I mean is IMU give a trigger to the camera. So camera actually open that shutter with the IMU so that you can have a good timings, right? So this triggers that API gives us some raw stream image and also the sync timestamp data. That's my question.
Yes, it does. And time synchronization is a very important aspect, as you mentioned. And yes, those are running on the same clock and giving hardware timestamps.
Thanks for that.
The next one.
You mentioned you can use with real odometry. What if I have some other pulse sensor, like GPS, for example, or can I have like covariance matrix from the pulse from the pulse estimation from the camera to use it in my own?
Yes, that's a very good question. So the way the fusion works, we are fusing a velocity measurement. So that can be used to also fuse different sensor streams or relative pulses. And we're using a translational velocity right now. And one has to provide, apart from the calibration, the extrinsics, one has to provide a measurement covariance for that measurement. Does that answer your question?
Well, can I have the estimation of covariance matrix of the estimated pulse from the camera?
You can get a confidence level, discrete information.
Levels of confidence?
Yes, it goes from low, medium, high. From low, medium to high, as you saw in the viewer. Okay.
On the tracking camera, it seems that most of the data that you're using is coming from the IMU. Can you clarify a little bit about what you're actually doing with the cameras?
We're using the images to do, on the one hand, visual tracking, frame to frame. On the other hand, they're an important source for relocalization, which is based on appearance, where we don't make any assumption on geometry.
Why are there two cameras? Are you using stereo?
Yes, we are using the stereo information, and that is to improve or better say not to have scale drift over time.
Sorry, I almost missed the last question. Okay, there's just a quick question about T265. Is it using just parallax information to obtain the depth of objects that in front of it, or it uses something else like the light emittance?
So it is using the yeah 435. So for the dense depth, we use the depth camera D435. You're right, for the tracking camera, we also have a stereo system. We are also able to estimate the depth or the distance of points. But in that case, I mentioned we're using a sparse algorithm, so it's only very few points.
So it's using the vision to understand distance to objects, right?
Also by integrating the IMU over time, the accelerometer, we get another estimate of the scale, which is somehow redundant, because we know it also works in the monocular case, but with the stereo system we obtain better performance and robustness, accuracy and robustness.
So for the tracking camera and real localization, did it actually build a map inside? And if so, how big can this map be and how robust is it to lighting condition changes?
Yes, that's a good question. It does build an internal map. We refer to it more as a relocalization database because it is only used internally. The map is not exposed and it is not dense, so can't be used for things like obstacle avoidance right now. Yes. Sorry, 1 second. I'm still trying to. Yeah. How big can the map be? I would have to double check, but if it's in the order of a few or several megabyte. And sorry, what was the other part? That was invariance to lighting, or?
Yeah, to illumination condition changes, to lighting condition changes.
Yeah.
I mean, if I light up a light somewhere, does it throw off the map, or does it still continue working?
So one light doesn't throw off the map. In general, talking about lighting, it works. We tested down to 15 lux, but about the invariance itself, that's more difficult to answer.
Thank you.
Yeah, please.
So the 15 millimeter is probably a good number already, but just see if you calibrate the camera with the encoder, would that be improved?
Sorry, can you say it again, please?
If you calibrate the camera with the encoder, because the encoder probably have better accuracy or something, would that improve
We mostly saw in the testing that it improves the robustness using the encoder. We already get a very good scale estimate from the stereo. And yes, it improves the robustness. The calibration itself between the two is an important step, as well as, of course, the calibration of the device, which is factory calibrated and validated.
The T265, what's the end-to-end power consumption? You said it was low power?
Yes, it's around 1.5 watt. 1.5.
Are we all going to get RealSense cameras today?
Maybe Roy can answer that.
So you can go to RealSense.com.
So do these cameras, are they still open for us to put like some more algorithms inside them, or I mean, like, is the architecture even open, and is there enough CPU available to do it?
So in this case of the T265, right now, you can't program the myriad yourself. We are evaluating that.
Sorry. Here, this one. This one.
Okay,
Okay,
go
for a
ahead.
stereo camera, how accurate can you determine the depth? Up to like centimeters or millimeters?
Yeah, so I had two numbers there for the 435. It was up to 30 millimeters at 3 meter, and for the 415, it was actually up to 15 millimeter at 3 meter. Yeah.
I have two questions about calibration. So for your 3D robot, I saw you have like depth camera and a tracking camera. Do you calibrate them together?
Yes. Yes, they have been calibrated with respect to each other as well, using all five images. So we used the 2IR and the RGB from the depth camera, and we used the 2 fisheye and solved that calibration problem.
Okay. The other one is like if I want to put one of the 265 onto like one of the AR glasses that we have and open up the case, will that throw off all the calibration or take it apart?
I don't know if I can answer that. Definitely, too much mechanical stress can degrade the calibration. I'm not sure if I can recommend opening the device. I did it a few times.
Yes. Can you briefly review positive and negative sides of structural light-based RealSense cameras and stereo cameras? RealSense camera. I don't know if RealSense has kind of light cameras.
So I can answer that.
So the D435 and the D415, they are both stereo cameras with passive matching, but with a laser projector that's actively assisting the stereo match for textureless or dark scenes. Now, the nice thing about a stereo camera is that you don't have interference between the two cameras. So if you overlap the viewpoints, the viewing frustrums of two of these cameras, then the projectors actually assist one another. So you can have better depth from actually having multiple cameras looking at the same scene. Whereas if you're looking at structured light or time of flight, then typically that type of camera will interfere with one another.
Okay, folks, let's go for the last question. And if you really need to talk to Phillip, please stay on and you can talk to him.
Yes.
So are these devices also used in your drone product? And if so, do you do height determination as well?
We tested it on drones as well, and it did a pretty good job. The accuracy was comparable to GPS. In a cube of 100 meters, we went up to 100 meters. Definitely, as you get further away, the accuracy decreases, or let's say the uncertainty increases when all the features are far away, but it can be used for height estimation above ground. Yeah.